volcano. Okay. Got it soon. Right, so the Kīlauea Volcano is on the Big Island of Hawaii, and it's this kind of topographically small volcano, but it's been extremely active in the past centuries. It sits on the side of the much larger Mauna Loa, and in volcanological world, this is kind of one of our best natural laboratories because this volcano is very active. And it's very well instrumented. And so we have a pretty good understanding of a lot of the basic things about the magma system here. And so this is kind of a cross section. So this dark spot here is the Kilauea caldera, which hosts a lava lake that you saw in my introduction screen at various points in time. We know that 1 to 2 kilometers down, there's kind of a magma storage region. There's slightly deeper magma storage region a couple of kilometers down, and then there's rift zones jutting out both directions from that crater that have fed a number of eruptions over the years, producing in some cases up to a cubic kilometer of lava per eruption. And so here's another video of the lava lake. This time a time lapse showing you a couple years of activity. So the same thing on my intro slide, but now you can see that this whole lava lake, which is basically sort of giving us a window directly into the magma system, is quite dynamic. And so what I'm plotting down here is the lava lake elevation over time from 2010 to 2018, so about 8 years here. And so you can see both in this plot and then the section of it in the video here, this lava lake is moving up and down by hundreds of meters over time. So as far as eruptions go, this would, a lava lake eruption in general is quite stable because it takes a pretty careful balance to kind of support a convecting lava lake. But clearly there's still a lot going on here. And then the end of this eruption, 2018, we had a massive, or volcanologically speaking, I guess, moderate-sized caldera collapse event. So that's what you're seeing in this video here. The whole summit region, couples of kilometers across, and I'll play that again if I can, basically collapsed. And it was doing so to feed this large eruption along a rift zone 40 kilometers away, which ended up actually damaging a number of residences that were located along the rift zone.
Is that black line at the right, the fall of the?
Yeah, so basically when this eruption kind of terminated in 2018, we had a sudden draining of the whole lava lake to feed this eruption here. And then essentially when you drain enough magma out of the reservoir that's sitting under this system, that's what caused it to collapse. So I'll come back to that more at the latter part of the talk. But what we're going to start with is actually the decade leading up to that final collapse. And ask how much can we learn about what the magma is doing during this time? So we're used to using various types of data to try to monitor volcanoes, right? So typically we can get a sense of ground motion, seismicity, capture shorter timescales, measure deformation on longer timescales too, insert GNSS, etc. Gravity data often quite useful. We can measure gas coming out of the volcano. We can actually see the activity, especially at a volcano like this. But often there's still kind of a big gap between these types of raw data we get and then actually figuring out what processes are really going on underground. So what's the magma doing? Is new magma coming in? How's it convecting? How are volatiles fluxing through this magma? And so what I'm going to show here is that by kind of looking carefully at the seismic signals coming out of this volcano, along with other types of data, we can actually get a sense for the, how the magma itself is evolving over time. So these seismic signals, I'm going to call very long period, or VLP for short, seismic signals. A bunch of these things occurred over this time period. For people who are used to looking at earthquake seismograms, this is a very abnormal looking waveform, right? It's remarkably nice harmonic. So there's a dominant frequency you can see here, which is about 40 seconds, which is quite long compared to a typical earthquake. There's some higher modes that are kind of buried in there too. And then you have this really nice exponential decay. And so this is the typical behavior of any sort of harmonic resonator. Essentially, you take a mass on a spring, let it go. And so the reason we're so interested in these, and I guess I should say, so these things are caused, well, they can be caused by a couple of things, but the one I'm showing on the right, it's kind of easiest to understand. Basically, we have this open lava lake, and occasionally stuff just breaks off the walls of this lava lake, large chunks of rock, and kind of perturb the whole magma system and cause it to resonate. And so these are valuable because they directly involve the fluid oscillating. So that gives us a very valuable probe of the magma itself. So these things had previously been cataloged, a couple thousand of them, up to 2014, kind of both manually and using in Markov models. But we found that these catalogs are a very good place to start, but they miss a lot of events, and they don't quite really get the resonant period and decay rate good enough for our purposes. So we basically just generate a new catalog using wavelet methods to try to kind of detect more events, and in particular, really get as accurate of estimates as we can of the dominant resonant periods and decay rates here. So I'll actually, in interest of time, skip over the details on that. So we generate, so we generate a catalog, and now let's see what this looks like. And so this is a video that Anna Barth, who's in the room, as well as some other people have done a lot of work putting together. Oh shoot!
Is this the one that has the sound?
Yeah, we need the sound. That's we might have. Was there sound in the key too?
Mm-hmm.
Oh.
If you unmute your computer, what will happen?
Okay, well, what you kind of see.
And you have to turn on that.
So that was probably a little hard to see, but the basic idea is, yeah, we catalog thousands of these things over time, and there are sort of systematic changes in the resonance period and the damping rate that are telling us something about the fluid properties of the magma.
Was the sound that you played sped up, or was
Yeah.
it the actual?
So actually, yeah, so why don't I,
We can try that one more time, maybe. And if everyone keeps their mouth shut, maybe it'll work.
wait, pause it for a second. So the sound you're hearing, the sound you're hearing there is basically some signal processing, but yeah, we're sonifying the waveforms from these events, and so there are kind of slight pitches in the sound. They reflect changes in that resonant frequency, and we're also kind of showing coloration and then the overall inflation or deflation of the summit system, and the change in lava lake elevation too.
But this was based on the 40-second main period that you saw in the signal.
Yeah, so it's kind of doing some processing to pick out that 40-second period, and then some higher modes, which still are actually quite long periods, typically 10 to 20 seconds that pop up in these events too.
Okay.
Which figure, yeah, higher order resonance. So I'll play that a little longer just to play it.
I think you have to put your speaker on again.
Looks like a modern German houses. At the end.
It's
there.
pretty ominous sounding at the end. No,
Yeah.
bad.
And so that ominous sound, part of that is coming from the inflation, so we're sonifying inflation too. Part of it's the change in the LP rates. But yeah, so that's actually kind of the question though. Can we use this kind of data to look for, say, systematic changes leading up to things like eruptions, beyond just what we might be able to learn from, say, pure depth ground information?
So coming back to what Michael said, the ominous sounding sound at the end, that was building, right? That was not an oscillation. Did you figure out where that was coming from?
Oh, so that sound, we, in addition to sonifying the very long period resonance, we added a sound to represent the inflation of the system as well.
So that was man-made. That was
okay. Yeah, so there's some.
That would be awesome if nature made that sound.
There's some artistry behind that. But yeah, again, the idea is just to emphasize that, things are clearly changing, building up to this eruption. And yeah, how much can we actually understand? So again, I mentioned when these resonance events happen, we have a pretty good understanding based on previous work by scientists at the USGS, myself, collaborators from Stanford, et cetera, figuring out that they basically represent, again, the whole kind of shallow magma system sloshing up and down and inflating and deflating its reservoir that's 1 to 2 kilometers deep. And so that's actually the inflation deflation of this reservoir is really what's generating the seismic signal we see. And we've also done some careful inversions for particular events to get a rough sense of how well we can constrain the geometry of the system. So things like the radius of the conduit, for example, viscosity of magma in the system. But again, for volcanologic purposes, what we really want to do is be able to relate these things to properties that might indicate, say, new magma or volatiles coming into the system. So signs of that would typically be things like magma temperature, bubble content, et cetera. But so here's the model we use to do this, right? So it's kind of a perturbation formula for uniaxial fluid flow here, where there's an inertial term. There's a buoyancy term on the assumption that we have a stratified magma column. So as you displace that, there's some restoring force. There's a pressure perturbation, which in this case is going to come in at the boundaries for whatever is triggering the resonance to start with, and then restoring force from compressibility of the reservoir itself. And then there's viscous damping, which in this case is typically going to be confined to boundary layers on the edges of the conduit. It's going to provide the majority of the damping. And then we also try to capture kind of as best as we can while keeping things simple enough that we can actually invert for these parameters what we know about the magma physics. And so basically, a lot of the properties of the magma in a system like this, where crystallinity it tends to be relatively low, are going to be controlled by changes in temperature, which is generally going to increase the viscosity, in some cases by up to an order of magnitude, with reasonable changes in temperature of 100 degrees or so. The amount of dissolved water also impacts the viscosity, which is not directly shown here, and then the porosity, so the bubbles themselves. Yep.
So the actual seismic source, is it emanating from the conduit or below or in the?
Yeah, so the
Right.
actual seismic source is almost entirely coming from this sort of roughly ellipsoidal reservoir
Yeah.
that we know is down there. The conduit is just a much less compliant structure, so it's a relatively minimal contribution.
Yeah.
There are some higher modes that are sensitive to, say, lava sloshing around and pressing on the sides of the lake a little bit, which also do kind of perturb the deeper system too. But yeah, basically it's that shallow reservoir.
And can you confirm that by locating the source?
Yeah, so the sources consistently locate, again, right around the depth where both seismic and geodetic conversions tell us the reservoir is. We've done a bunch of seismic conversions to see how well we can constrain the source of these things. There's only about 12 near field broadbands, which are what these events show up in best. So it's a little hard to, we can't resolve it too well beyond it seems roughly spherical. There's some indication that there might be some involvement of dike-like structures as well, possibly jutting out kind of a main magma storage region. But it's generally pretty concentrated in around 1 to 2 kilometers depth. Some sort of blob-like magma reservoir. Of course, never resolve these things in too much detail. But I guess from the perspective of this resonance, it mostly kind of cares about the overall compressibility of that magma reservoir, and so based on the shape of that, how much of an elastic restoring force there is each time you pressurize the thing, which we have reasonable constraints on that.
Can I ask a question about that equation you showed there? There was a little h in that first term. What does that refer to for the buoyancy?
So this h here is referring to the perturbed height of the
lake,
the magma column, or if you're at the surface, it would be the lava lake.
Right.
Lava lake surface. So basically this is saying if we have some vertically stratified column and it's shifted up or down a little bit, you've effectively changed the density based on what the density gradient was at that point. So this kind of perturbation formula that's valid for small oscillations.
and then via the pressure you get the size of the conduit. Then R0. The conduit pressure there, the equation at the bottom, the R0, R naught.
That's radius. So this is kind of a cross-sectionally averaged pressure. So R0 is the radius at the bottom of the conduit specifically. And the assumption is for now the radius could be variable with.
So I don't want to go into too much detail, but when you look at this periodicity that you have there, it's almost monochromatic. If you change what component of your system, the way you show it there, would change this the most? Is it most sensitive to the conduit, to the lake, to the reservoir?
Yeah, so it turned out the period is sensitive to a variety of things. The first order, the overall density of the magma column matters quite a bit, but also the density stratification affects the period. Changing the length of the conduit, of course, impacts the period quite a bit too. Period has some sensitivity to conduit radius, but mostly the conduit radius is going to impact the damping, the amount of viscous damping you get. And there's a whole kind of parameter space I could show later for exactly what impacts the system.
Okay.
But yeah, there are quite a few things that matter. And so, and obviously we are not going to be able to uniquely constrain all of those. So kind of have to keep that in mind as we go through. And I'll have a plot soon that shows some of that anyways. And then the other important thing, we know magmas in general are, especially basaltic magmas like this, typically contain a couple volatile species. So at Kīlauea, it's going to be a mix of water and sulfur species, which typically come out shallower. So a couple 100 meters depth, and then CO2, which can come out multiple kilometers down. And so there's some kind of complex relation between how much exhaled gas you actually have based on how much water, how much CO2 you have sitting down there. And so we can say, well, what if, for example, we have X amount of CO2 at depth, which is what I'm showing in this yellow line here. And in the shallow part of the system, it's essentially all exhaled. So that's all going to be in a bubble phase. You can see the water line here. A lot of this water, as we move deeper down, is going to be kind of dissolved in the melt. And so this is one of the things we're going to want to invert for, is like how many volatiles do we need at a given depth to explain the observations. And of course, that in practice, what those are giving us is, say, the density of the magma, how that density is stratified, and then the viscosity of the magma and how that's stratified. But anyway, when we run this model with example parameters, you see it basically pushes out a nice harmonic oscillation, just like the sort of seismic waveforms we see. And then the other important constraint we have is we have a sense for how the overall pressure in the shallow reservoir is changing, which we can get from geodetic inversions. And so there's some extra complexity that's accounted for here. I'm not going to go into too much. But yeah, essentially, this gives us constraints on the pressure of the reservoir. So now we have our catalog of periods and quality factor of the resonant seismic events. We also have the lava lake elevation data to throw at these inversions. We have a sense of the lava lake radius, which evolved over time due to all these rockfalls. And then we have the geodetic inversions. So this is kind of all the continuous data we have. And the goal is to use that to pick some parameters to invert for about what's changing in the magma. And so if we say the things we're interested here, magma temperature. So we can ask, as we say increase, in this case, assuming kind of a lump temperature across the conduit, if we increase magma temperature, our quality factor increases a lot, which means this resonance doesn't decay nearly as quickly. And it has some impact on period 2. We can tinker with the kind of the total amount of volatiles there, but also with how the volatiles are stratified, and that's going to impact both the period and the quality factor. And then this lava lake data we kind of can prescribe based on observations. And so what do we get out of this? Well, so here's our inversions for magma temperature. So the x-axis here is jumping between about 1100 and 1300 degrees C. And I guess the first thing I want to point out with any of these plots, there's quite a lot of scatter, of course, and then these shaded regions are an indication of error bars. So there's a lot of uncertainty in what the absolute value of these parameters are at any given point in time. So the main thing we're looking at is the relative changes. So you can see there are pretty stark changes, actually. So we see this big drop in temperature, for example, leading up to, this is a rip zone eruption in 2011, which is actually maybe not what you would expect leading up to an eruption. But typically, if you thought the eruption was caused by an influx of new magma, for example, maybe that temperature would be going down. But then there are times where we do see the temperature kind of creeping its way up. There are times where the temperature drops quite sharply. So right here, for example, which can really only be explained by, say, a downwelling from the lava lake, where you can have magma kind of stagnating, cooling quickly, and then suddenly fluxing its way down through the conduit. But we really don't see any consistent changes actually near the later part of the eruption. So there's not really evidence from magma temperature, at least in the shallowest part of the system, that we had any significant influx or anything like that. And then the volatile contents too, you can see, again, we're not so much focused on the absolute values here. We're kind of looking at how things are changing over time. So you can see quite a bit of change over time. So we look at 2015, for example, leading up to this intrusion event where you push the new dike into the ground somewhere. We see an influx of volatile contents, which maybe is indicating at least some depth in the system. There might be some new magma moving in, or at least a change in how effectively the magma is circulating around. And then there's also kind of a gradual increase leading up to 2018 here. It's, again, subtle within the error bars, but this is the kind of thing that, hopefully, especially if we can improve methods like this, we can really start thinking more about, are there signals of actually things like gas building up in the system due to magma recharge, things like that. And I guess I'll point out, so the bottom part is the stratification of volatile content. And so the main takeaway here is that over most of the timeline, these values are positive. And so this is telling us that there's quite a lot of gas sort of built up in the lava lake, basically relative to what's down in the reservoir, which in some sense is not surprising for an open system like Kīlauea, which we know is constantly convecting. It's got to be what volcanologists consider sort of far out of equilibrium. But it's maybe a little surprising just how much disequilibrium you need. But yeah, it seems like our modeling is telling us there's really quite a bit of gas built up in the lava lake here. So maybe, I'll quickly get to the conclusion on that. But yeah, so the conclusion from that part is just that, by kind of combining a couple of these types of signals with some modeling, we really can see in situ changes in the actual magma properties that we're interested in. There are big error bars on doing this right now, but as we get more and more types of continuous data we can bring in, so better continuous gravity data, for example, maybe this is really a way forward in understanding what the signals we see in volcano monitoring mean. Maybe this will be a good questions point.
Do you want to tell us about John?
I got the sense from your temperature data that it's a temperature we couldn't directly measure. Like your inversions provide us information on out of scene parts of the system, correct? And so is there any correspondence between surface temperature measurements, like with infrared or anything like that?
Yes,
with your data? Because it seems pretty hot.
Well, actually, so some of these temperatures, so we have a couple geochemical temperature estimates that have been published. There are more estimates available that haven't been published yet, but they actually do generally kind of line up quite well with what we're seeing.
Okay.
But these, depending on whether you're looking at the glass or the melt inclusion temperatures, it's a little unclear exactly what depth and the sensitive the system those are probing, but it's probably more representative of a reservoir temperature.
Yeah. Okay.
But those do typically sit, around 1150-ish. So kind of what we're seeing is there are some values that might be spiked above that slightly. In particular, here there's a higher spike, which I didn't go into much. Part of this could be that there's kind of some change in the geometry of the magma system during this time. It could explain that, but in particular, these drops, for example, those things probably real, and so that might again, some of those, especially where there's drops on short time scales, you really kind of need convective downwelling, so the only way to explain that. But where there's like a gradual buildup here or here leading up to this eruption. Yeah, I mean, those are, they're kind of within reason, and I guess the infrared temperatures, those can be quite variable at the surface of the lava lake, but they're often like many hundreds of degrees lower than the actual.
Yeah, okay, that answers my question. And then just the peaks stood out to me as being pretty hot, not the running average that you got there.
Yeah, and again, I would say, yeah, there are huge error bars on this, of course. So I wouldn't read too much into any one data point that's like.
Yeah.
No.
Okay, thank you.
What's the main source of extirpation? You said it was stuff falling in lava lakes, but does that say?
So, yeah, so that's one source, stuff falling into the lava lake. Sometimes it seems to be sort of bubble slugs that rise, and they can perturb the system a bit as they're rising, and also if they burst the lava lake surface, they can perturb it. Some of these signals have an opposite polarity of the rest and don't seem to have a surface expression. And so the thought is that they might be either some kind of a bubble slug event happening at depth or some transient dike opening feature or something in the subsurface. Not
Could these systems be forced? I mean, could you sort of exert a forcing on it, bring like a fiber size in or something like that? Examine what the response of the system is as you change the frequency of force.
Yeah, I mean, you certainly could, and I've actually tried to look at whether teleseisms do that. And it's a little tricky to see if they're really causing resonance. And I guess ideally you need to hit it. So if you want to see
Around
this,
40 seconds.
yeah, this dominant period, which I think is longer than a typical vibro size, right? By quite a bit probably, but
Well, but I mean, presumably you could propose or have any kind of frequency if you wanted, but I don't know. I just sort of wonder if these things were probable by sort of external means, right?
I mean, I think they are, and there is, so this summer there is going to be a vibro size nodal deployment active source experiment out there. I don't know if very many people have tried to look intentionally though for triggering this resonance thing. I saw like some indication that teleseisms might be doing it, but not statistically significant enough that I would.
You could get it to plow up. I'm joking.
Dorian?
If your resonance is in the tens of seconds, maybe noise from a big storm, could that also force it?
Possibly.
Observe something like that?
I mean, the oceanic microseism in general is quite strong in this area. Right around periods of 10 seconds. But from my perspective, that's actually more of an annoyance because it typically kind of buries the higher order resonances that I would otherwise like to be able to model the same way, kind of, model this fundamental resonance. Because basically different resonant modes will have slightly different sensitivities to different parts of the magma system. So if we could invert for other ones as well. And then, so I didn't really go into it, but to do these inversions, for example, I had to assume that a lot of things are fixed. So I assumed that there's just a fixed ratio of, say, water to CO2 contents, which is probably about right for the parent magma, but probably not right in the shallow part of the magma system where things are constantly fluxing around. But yeah, the more constraints we bring in.
Did you get a sense of the size of the magma chamber? Are your figures to scale roughly?
Yeah, so I tried to draw those pretty much to scale. The volume of the magma chamber itself, I think, is around 4 cubic kilometers. So a radius of about 1 kilometer. And yeah, the lava lake and conduit here are also drawn sort of roughly to scale. We have actual digital elevation models from a couple of times where it fully drained of the lava lake, at least not the conduit underneath it. There's a little more uncertainty in what the conduit's actually doing. And I think there's some evidence. So basically when we do these kind of inversions, we see some things that just don't make sense. Like at the earliest part of the time period, if we assume everything else is equal, we end up needing to put ridiculous amounts of volatiles in there to produce the resonance. So I think that's telling us that the geometry of the system is kind of changing appreciably over time. But it's tricky to uniquely invert for that, basically.
Josh, did you want to tell us about the collapse events too? I think we probably have, that's 10 minutes.
10 minutes. Okay, I'll give people a quick pitch on the collapse. So at the end of this eruption, right, we had this really nice collapse sequence. And so all these colored plots on the bottom are either GPS data on the bottom here or tilt the top view. And so you see this really nice sawtooth pattern. So what's happening there? I have a cartoon. Oh, actually, here's another video. So the red circle here is inflation of the magma resonance.
What's he created this?
So the whole time frame here is about 3 months.
Pretty long time.
Yeah, so each. Yeah, so what you just saw was about 3 months, so May over here to August, which is how long this kind of caldera collapse, so the video I showed earlier lasted. And so each of these little sawtooth spikes is happening about a day after the previous one. And so this is basically an earthquake sequence, but compressed into several months. And we can see this really nice buildup of seismicity in between each event that ends up outlining nicely this collapse structure. So essentially what's happening here is as we started draining the magma reservoir, the region of rock above that eventually just starts collapsing in. And because there's rock on rock contact, it's essentially an earthquake system. And it turns out this isn't something that's unique to Hawaii. This has happened basically every time we've seen a caldera collapse, which there have been a number of now. There's some sort of episodic earthquake sequence like this. And it turns out that's actually important, one, because these earthquakes cause surges in eruption rate, but also each time you have one of these, you're dropping the central piston down and you're pressurizing your magma reservoir. And so that's going to allow the eruption to keep going potentially a lot longer than it otherwise would by keeping the magma reservoir pressurized. So people have done a little bit of work to try to kind of understand the mechanics of these systems, but typically pretty simplistically. And so what we want to do is kind of look at them from an earthquake mechanics perspective, leveraging all the understanding of fault friction and stuff that people have developed over the years to see how much we can constrain about these fault properties, because typically rocks and magma systems are quite heterogeneous. For example, you can imagine you have, say, a velocity strengthening region at depth near the reservoir where things are quite hot. That changes a lot with depth. You're just essentially compressing a crustal geotherm into a much smaller area. It also gives us a way to look at things like the dips of the faults and how that impacts the mechanics and so on. So I've basically been doing these sort of earthquake sequence simulations, which I won't get into the details too much in the interest of time. Again, this is kind of we're taking methods from typical earthquake mechanics studies and trying to see how they apply in this setting. So here's an example of one of these simulations, loosely targeted to kind of match what we see at Kīlauea. And so what you're seeing is colored by stress, in this case, the RZ component of stress, and then the reservoir is colored by pressure. So I'll kind of stop it at a good spot. Okay, so here is before anything's really happened, our reservoir is draining, so you can see it's quite depressurized, and we're starting to build up a lot of stress in the rock around it and on those faults. Okay, so what you see here is at some point we start having this creep pulse kind of migrate up the fault, where we've actually started to have a bit of slip. And that moves upwards at an increasing rate. And then when this thing actually hits the surface, we suddenly have the actual collapse earthquake. And so now we've brought the reservoir pressure back up again. We've relaxed a lot of the stresses in the surrounding rock. And this is creating kind of a diagnostic pattern. So here's the results plotted up, maybe how we more typically look at earthquake simulations. So you can look at, say, the slip velocity on the fault over time. Each of these earthquakes in this case is giving you a little over a meter of slip. You can see the cyclical pressurization of the reservoir that very closely matches the geodetic data we get. So the idea is to kind of see what we can learn from these kind of simulations now. So again, this one is roughly tuned to kind of match what we see at Kīlauea. And so one interesting takeaway is we're actually getting quite a bit of appreciable amount of creep at the lower part of this fault, which seems to sort of line up with the distribution of microseismicity. So here I'm plotting previous catalog, which, Shelley and Thalen 2019. So right around a little less than a kilometer depth, we get this scattering of seismicity building up between each event, which really hasn't been fully explained yet. But I'm hoping we can kind of relate a lot of this to the stress changes that are happening as a result of both the reservoir inflating, creep on the fault, some combination of those forces. We can ask what happens if we put a little bit of dip on the fault, because in general, when people look at these ring faults, they actually tend to infer that they're dipping quite a bit. But it turns out even if we put very, very tiny dip, so 0.5 degree inward dip, it really changes the overall mechanics. We're just building up normal stress very quickly. And so instead of having a uniform earthquake cycle, we get these intervals that quickly increase a lot with time. But that's actually consistent with what we've seen at some other volcanoes.
Do you mean actually 5 degrees or 5 degrees off vertical?
So 0.5 degrees off vertical.
Yeah.
So like very near
That's
the
what I
vertical,
thought.
but just
Right.
yeah. But even that tiny bit of dip really makes a big difference. And of course, in reality, there's inelastic stuff going on to it that's
Right.
not accounted for here. But the point is, it's like remarkably sensitive to that. We can look at the frictional parameters too, which kind of skip over that in the interest of detail. But yeah, I mean, basically, if we tinker a little bit with, say, the pore pressure or the normal stress, particularly at the lower part of this fault, which we might expect to change a lot in volcanic settings because we got all this hydrothermal stuff going on, we can really kind of significantly change the collapse mechanics that come out of this system. And so, yeah, this is still kind of exploratory phase right now, figuring out both what we can constrain about fault properties in a particular eruption and kind gaining a more general understanding of what controls these eruptions. But yeah, so maybe we'll talk about it a little bit.
At the other places that you mentioned that have the caldera collapses, is the like